Hello everyone. Today I am going to explain about the electrostatic discharge. Okay. So here first we have to know what is electrostatic discharge and what are the different testing models for this electrostatic discharge and what is the protection network we are going to use in the circuits, in the integrated circuit to avoid the problems created by this ESD. Okay. So here first I will consider uh, what is the effect of this ESD. Okay, so there is a growing interest in the effects of ESD on the performance of semiconductor integrated circuits because of the impact ESD has on production yields and product quality. Okay, so electrostatic discharge is playing a vital role on this production yields and production quality of integrated circuits. Okay, so the main ESD problem can arise or increases due to the fact that nowadays we are producing that high-speed devices and at the same time very small devices. Due to that, the ESD problems are increasing. Okay, so here ESD problems are increasing in the electronic industry because of trends towards the towards higher speed and smaller device sizes. Okay, so because of that, there will be increasing in the effect of this electrostatic discharge. Okay, then what is electrostatic discharge? Electrostatic. Okay, and what are the different charges that are present in this electrostatic discharge means here static charge is the main key point or key charge that will place that will causes the electrostatic discharge. Okay, then what is static charge here? Okay, static charge is an unbalanced electrical charge at rest. Okay, what is static charge? Static charge is an unbalanced electrical charge at rest. Okay, static, it cannot move. Okay, cannot move. That is called as, that will be unbalanced electrical charge at rest position is called as what? Static charge. Static charge is an unbalanced electrical charge at rest. Static charge is created by insulator surfaces rubbing together or pulling apart, right? One surface gains the electrons while the other surface loses the electrons. This results in an unbalanced electrical condition known as static charge. Okay, so static charge is created by insulator surfaces rubbing together or pulling apart. One surface gains electrons while the other surface loses the electrons. Okay, so this result creates an unbalanced electrical condition known as what? Static charge, right? So this is about static charge. Now we will see what is ESD, okay, or what is electrostatic discharge. Okay, so when a static charge moves from one surface to the another surface, it is called as what? Or it becomes the electrostatic discharge. Okay, I already told that the major charge that will causes the electrostatic discharge is what? The static charge. Okay, so when a static charge moves from one surface to another surface, it becomes an ESD. Then when this ESD will take place, okay, the electrostatic discharge will take place between the two surfaces that have different potentials. Okay, that have different potentials, right? ESD is miniature lightning bolt of charge that moves between the two surfaces that have different potentials. Okay, then when this electrostatic discharge will take place means whenever the ESD is taking place between the two surfaces means compulsory the voltage difference between the two surfaces must sufficient to break down the dielectric strength of the material between these two surfaces. Then only the ESD will be obtained. So that is the point here. It is very important. It can occur only when the voltage difference between the two surfaces is sufficiently high to break down the dielectric strength of the medium separating the two surfaces. Okay, then what is this point and what is meaning of this point means here? Okay, so if you consider two surfaces, suppose these two are the two surfaces here we have. In between, I am placing my dielectric material. Okay, so if the dielectric material is present, there is no flow of charge between one surface to the another surface, because dielectric surface or dielectric medium is nothing but it is an insulating material. Okay, this insulating material will opposes the flow of charge. Okay, so therefore we have to remove this insulating material strength. Okay, for that purpose, so the voltage or voltage difference between the two surfaces is sufficient to remove or break down the strength of the dielectric medium. Then only there will be a flow of the static charge from one surface to the another surface. Okay, so that's why it is very important point to know about this ESD, electrostatic discharge. Okay, so here we have 3 points mainly. One is what? When a static charge moves from one surface to the another surface, that is called as what? Electrostatic discharge. The second point is the electrostatic discharge is nothing but it will take place between the two surfaces. They consist of some potential difference between them, or the two surfaces must have different potentials. Okay, so the third point is here, it can occur only when the voltage difference between the two surfaces breakdown is sufficient to break down the strength of the dielectric medium. Then only there will be a flow of this surface static charge between one surface to the another surface. Okay, so this is the third one, right? So, and finally we have here, when a static charge moves, it becomes current. It becomes a current that damages or destroys the gate oxide, metallization, and junctions. So if you consider any flow of charge from one point to another point, generally we will consider as a current. So here also there will be a static charge movement from one surface to the another surface. Whenever it is taking place, then automatically there will be a current is present due to this static charge. Okay, this current will damages the whatever the we have metallization, and at the same time the gate oxide between the gate and at the substrate. Okay, and junctions also. Okay, so that is the effect of this electrostatic discharge on our transistors. Okay, and at the same time different junctions, right? So when a static charge moves, it becomes a current that damages or destroys the gate oxide. Whenever a gate oxide is destroyed, okay, what is the effect of it? Okay, if you consider, it is the transistor here. If you consider this one is the gate, this one is SiO2, that is silicon layer, silicon dioxide layer, and this one is the gate, this one is gate, and this one is the substrate. Okay, so between this substrate and gate, SiO2 is there. So if this, what we call it, this electrostatic discharge, if it destroys the gate oxide, that is SiO2, then the gate and source will be overlapped. Okay, so the gate and source will be directly connected. Okay, so it will causes it will changes the electrical properties of the mass transistor. That's why here we have to keep protecting this gates or gate oxides, and at the same time metallizations and junctions from this ESD. Okay, so what is protection network and all those things we will see here, right? So this is about what is ESD means, right? Right. So in how many ways this electrostatic discharge will obtain? We have 4 ways or 4 different ways in integrated circuits this electrostatic discharge will obtain. The first one is a charged body can touch an IC. Okay, a charged body can touch an IC means whenever a human body or if I touch with this finger on the IC while fabricating or while manufacturing, okay, then there will be electrostatic discharge will be takes place. Okay, because here there will be some potential for the human body or the charged body also. Okay, whenever if they touch that IC, there will be a flow of or the charge movement will take place, static charge movement will take place from one body to the other. Okay, then that is nothing but a ESD. Okay, so that's why in the fabrication, while doing the fabrication process in the fab, they will take one suit. Okay, so to avoid this electrostatic discharges, to avoid all the effects of these static charges, they will consider they will wear a suit while manufacturing or while fabricating ICs. Okay, so that's what the first one where we'll get this electrostatic discharge. A charged body can touch an IC, and next one is a charged IC can touch a ground surface. Okay, a charged IC when touches a ground surface also, there will be a movement of this static charge from the IC to the surface or surface to the IC. Okay, next one, a charged machine can touch an IC. When a charged machine can touch an IC means the charge that is present on the machine, the charged machine will move to the IC so that there will be electrostatic discharge will taking place. And another one is the electrostatic field can induce a voltage across a dielectric substance to break it down. Okay, so these are the four ways how we will get electrostatic discharge, right? Electrostatic discharge is one of the most prevalent causes for chip failures in both chip manufacturing and field operation. Okay, chip manufacturing means in the fabrication, I told that to avoid all this ESD effect, so they will wear separate suits for to manufacture or to fabricate the ICs. Okay, so that is the point. Electrostatic discharge is one of the most prevalent causes for chip failures in both chip manufacturing and at the same time on the field operation. Field operation means whenever they are using in a device. Okay, then at that point also there will be a failure will obtain. So out of this, the main cause or the major cause is nothing but electrostatic discharge. Okay, so ESD can have serious determinantal effects on all semiconductor ICs and the systems that contains them. Okay, so this is the main effect that is shown by this ESD on the electronic industry or semiconductor integrated circuit industry. Okay, so directly there will be a failure of that chip will be takes place whenever this ESD is taking place, right? So that ESD can have serious detrimental effects in all the semiconductor ICs and the systems that contains. Okay, now we have the different testing models of this ESD. Okay, so we have different models for ESD testing. First one is the human body model, that is HBM in short form, and next one is the machine model, that is MM, and next one is the charge device model, that is CDM. Okay, human body model HBM, machine model MM, and charge device model CDM. Then how we can test this electrostatic discharge and how we can discharge that one to avoid the effect of that on the device under test. Okay, so here the human body model, a human walking across a synthetic carpet in 80% relative humidity can potentially induce 1.5 kV of static voltage stress. Okay, so whenever a human body is walking on the carpet, synthetic carpet, it produces 1.5 kilovolts of static voltage stress. This is nothing but what? It is also a electrostatic discharge here. And how you can avoid this one is nothing but here, if you observe this, here we will place in between this electrostatic discharge and the device under test. DUT means device under test. So we are going to use 1.5 kilo ohm, 100 picofarad resistors and capacitance respectively to discharge that electrostatic or the static charge. Okay, so that is the model what we are going to use to test this human body or electrostatic discharge. Okay, so in the human body model, a touch of a charged person's finger is simulated by discharge of a 100 picofarad capacitor through 1.5 kilo ohm resistor. Okay, so what is this point? Whenever a human body, a charged finger of a human body touches, so what is the effects? Here we have more amount of static voltage stress will be obtained. The stress will be suppressed by using what? 1 kilo ohm and 100 picofarads. Okay, resistor and capacitor to discharge that electrostatic discharge effect. Okay, so that is what here. In the human body model, a touch of a charged person's finger is simulated by discharging a 100 picofarad capacitor through the 1.5 kilo ohm resistor. Okay, so this is human body model. Next one is we have, and it is important that some protection networks to be designed into the IC circuits of the chip so that the ESD effect can be filtered out before its propagation to the internal logic circuits. Okay, so if you consider, we will see the product, what is protection network and where we use that. But here it is important that some protection network be designed into the IC circuits of the chip so that the ESD effects can be filtered out before its propagation to the internal logic circuits. Okay, so the protection network we'll see later. The effective protection networks can withstand a high as 8 kilovolts human body model electrostatic discharge stress. Okay, so next one is the machine model. In addition to the human handling, contact with the other machines can also causes the ESD stress. Not only human body at the same time, from a charged machine, if it touches the ICs, then there will be a electrostatic discharge will take place. That is also called as what? The electrostatic discharge stress. Okay, in addition to the human handling or human touches, contact with other machines can also causes the ESD stress. Since body resistance is absent, the stress can be more severe with higher current levels. Okay, and here we are using what? 200 picofarads to test this machine model. Okay, next one is the charge device model. It is intended to model the discharge of the packaged integrated circuits. The charge can be accumulated. Okay, suppose after if you consider or after manufacturing of or packing of that IC, if there is a electrostatic discharge is present, so how we can discharge that charge will be is nothing but the charge device model. Okay, this is the diagram that shows the charge device model. Okay, it is intended to model the discharge of the packaged integrated circuits. The charge can be accumulated either during the chip assembly process or while it is shipping to the shifting tube, while it is in the shipping tubes. Okay, so in both ways here, while manufacturing or assembling process, or while shipping these ICs after packing, we will get this effect, electrostatic discharge effect. This is another model what we have, that is charge device model. Okay, so this is the simplified lumped element model of human body model electrostatic discharge and machine model electrostatic discharge testers. Okay, and here it is mentioned that the capacitance in picofarads for human body model is 100, for machine model is it is 200, and stat resistance is RS, it is 1500 and it is 25. Okay, so like this we have different models for the electrostatic discharge. Okay, so now the next one is what is this protection network? Here we have the protection network. Why we have to use this protection network? Suppose if I have an IC, okay, if I have an IC integrated circuits and it consists of different devices, internal circuits, different NAND gates, NOR gates, flip-flops, and all those things, it will be accommodated. Okay, but whenever I am applying the input for this circuit, if I want to apply the input here, that input I cannot directly send from the input device to the circuit. Okay, circuit or IC, internal circuit of the IC. Okay, so to avoid this electrostatic discharge, what I will do is in between this input and the IC, this one is the integrated circuits, what I have. Between this input and this integrated circuits, I am going to use the protection network. I am going to use the protection network. Then what is the importance of this protection network? Okay, so if any electrostatic is a static discharge is taking place at this input side, then that will be avoided, that effect will be avoided by using the protection network. The name itself, it is there, it will protect the input value or the input signal from the electrostatic discharge. Okay, so that is the importance of this protection network. Okay, so the name itself, it is there, protection network. So in between that input and input device and at the same time the IC, so we are going to use the protection network to protect the effect from the effect of electrostatic discharge. So that is called as what? Electrostatic discharge protection. Okay, so here we have electrostatic discharge protection, right? The protection network usually consists of a diffuse resistor diode structure. Okay, so the protection network generally consists of what? A diode and a resistor. Okay, diode consists of capacitance. Okay, the capacitance diode combination will clamps the diode and resistance combination will clamps the signal. Okay, so here that is the point. The protection network usually consists of a diffuse resistor diode structure. The input resistance is normally between the between 1 and 3 kilo ohms. Here you can observe here, this is the input pin. And this is the model of a simple model of protection network. Okay, that consists of what? A resistance here. Okay, so a resistance, resistor and a diffused diode. Okay, so in pulse and digital circuits, we have learned that what is this clamping circuit. Okay, so this clamping circuit is when you are going to use a diode and a resistor combination, okay, with capacitance, that is called as what? Clamping circuit. Okay, so here also where we are getting this capacitive effect means in the diode itself, right? So the protection network usually consists of a diffuse resistor diode structure. The input resistance is normally between 1 and 3 kilo ohms. This resistance in conjunction with the capacitance in diffusion. Okay, what is here? The resistor and capacitance including with the diode will give the clamping, right? So here I am showing that the resistance and the diode, but I am not showing any capacitance. So where that capacitance is? That capacitance is nothing but the diffused capacitance of the diodes. In combination with this resistance will clamp the input signal to a higher level, that is higher than this electrostatic discharge voltages. Okay, so like that it will conduct, it will transfer the signal from input device to the actual chip. Okay, so this resistance in conjunction with the capacitance in diffusion diodes and gate capacitances in input transistors integrates and clamps the voltage to a safe level. Okay, in essence, the diodes clamp the signal level within a voltage range in order to minimize the impact of ESD. Okay, this electrostatic discharge impact can be avoided by clamping the signal or the input signal while reaching the IC. So we have to clamp that input signal to this range of voltages, that is minus 0.7 volts to VDD plus 7 volts. So if this voltage is present in between this minus 0.7 volts and VDD plus 0.7 volts, then there is no effect of this electrostatic discharge, and that is provided by our protection network. Okay, so this is our example of protection network. In order to not permanently damage the diode structure, the current through the diode should be limited to less than several tens of milliamperes. So to permanently protect this input signal from the ESD and at the same time without damaging this diode means we have to maintain a less amount of current across the diode, that is several tens of milliamperes. Okay, so this is what we have the interaction to the production network. Okay, mainly the production network consists of a resistor and a diffused diode. Okay, so the diffused diode means it consists of a capacitance also. The resistor in combination with this capacitance clamps the input signal to a higher value so that it can avoid the problems from the electrostatic discharge. Okay, so that is what the production network, and it is very important, that is electrostatic discharge protection. Now we have another advanced model of this protection network. Okay, the protection network, the use of additional thick oxide NMOS transistors as shown in figure, this one, has proven to be very effective and yielded protection in excess of 3 kilovolts in the human body model electrostatic discharge test. Okay, so if you use this the use of additional thick oxide, that is NMOS transistors, okay, it will give more protection from the electrostatic discharge for the input. Okay, so in this circuit, whatever we have here in this circuit, M1 is the thick oxide punch through device, and M2 is a thick oxide NMOS transistor. Okay, and M3 is a thin oxide NMOS transistor. Here M1 is what? Thick oxide punch through device, and M2 is a thick oxide NMOS transistor, and M3 is nothing but thin oxide NMOS transistor. Okay, that is operating in saturation mode. Right. For positive input transients, M1 and M2 have threshold values of 20 to 30 volts. Okay, so this is the advanced or modified production network as compared with the previous one, and it is very advantageous as compared with the previous diode resistance production network. Okay, thank you for watching. Subscribe our channel.